Did we do the wall last one?
Yeah, I was thinking we do something like 41 or 40. Let's do 41. We haven't done a cone yet. So 41 is about a cone. What's wrong, Lillian? What's the matter? We do be living in a society with shapes. Okay, so 41.
Oh my god. I started singing it and she
You got a cone. And as usual, to answer these questions, you have to kind of carefully read the wordies.
The word birdies?
Because this says, well, first of all, any cone, we're talking about the volume, right? So the volume is, there you go, 1/3 times pi r squared, which is this base area here, and then times the height, which is, so a cone, you can kind of think of a cone really as a pyramid with, where the base is a circle, which in a sense is a polygon with a billion sides, kind of. So anyway, it's the same formula. So anyway, it's all gone. No more scary box. Lily said she's afraid of the cereal box, so there you go. It's all gone. No more nightmares. No more lemurs. Okay, so
Johnson and Johnson's no more lemurs.
yeah, this says that the base diameter, is always equal to the height. Okay, so this distance is always equal to this distance. Now the question is going to ask us about the cone's radius. How fast is the radius changing at the moment when the radius is full? So the question is, do I want to rearrange this equation so it's all h's? I shouldn't say rearrange, I should say substitution. Should we do a substitution? You guys see why I don't want there to be r's and h's in there? Or is that not obvious? Not obvious. So the reason is, won't our life be easier? They're giving us information about diameter is double the radius, right? They're giving us information about how the radius and height are always connected. And so we always want to make our life easier, right? So we always want to make the problem as simple as you can make it.
Yeah.
And if we can do a substitution, right? If we can replace the h's with r's, or r's with h's, then there will only be one variable on the right-hand side, and that would certainly make things easier for us, right? Does that make sense? Does that help? Okay. So if this is r, how tall is it? How does the height compare to the radius?
Well,
It's 2 times r. So the height is twice as big as the radius. So since the problem is eventually asking us to talk about the radius's rate of change, I'd like to have this be all radius, all r's, right? So what I'm going to do is replace the h. Long story short. So height is equal to 2r. So let's simplify this formula. So 2 times 1/3 is 2/3. And then r squared times r is r cubed. Okay? So now let's take the derivative. B prime is equal to, now this is nice, no more product rule needed, right? Or I might have had to use the product rule. Basically the key here is that if they give us this information about how the, say the radius and the height are kind of constrained to move together, then you can opt for the substitution. So 3 times 2/3 is 2. So 2 pi r squared. What am I missing? I almost forgot. R prime. Remember, we're taking the derivative with respect to time. If you want to be really technical, you're like, oh, what am I doing to both sides of the equation here? What you're doing is applying this operator to both sides of the equation. And we usually don't write this step out, but if you're wondering. You're thinking, oh, isn't all of algebra kind of based on this idea? Not all of it. Most of the algebra we do is based on this idea that you're doing the same thing to both sides of the equation. So that's what you're wondering. That's what we're doing. Okay, so the problem tells us some information. There's a 12 pi in there. Where does that 12 pi go? Yeah, at the very beginning of the problem, you might have written v prime is 12 pi because it reads the cone's volume is increasing at a constant rate of 12 pi cubic feet per minute. So that you can translate that into that mathematical statement and then sub it in. Here we go. And it also tells us the moment, because you can see, right, this depends on how big the cone happens to be at this moment, right? If the cone is really big, the answer is different than if the cone is really small. So it says at the moment when the radius is 4. So you plug 4 in for r. We're solving for what's the rate of change of the radius. So that's the only thing left that's unknown, so we feel good about that. Divide both sides by, let's see, 16 times 2 is 32. Pi. So cancel it eventually, cancel it eventually. But most divisible by what? 4. So 3/8. That's a nice number. Oh, let's put unit. We got to put units in. So if they were giving us the volume in cubic feet per minute, then what would the units of this be? Just feet per minute. We want, so the volume is cubic, is like a three-dimensional property, and the radius would just be a one-dimensional property, so like feet as opposed to feet cubed. Okay, so there you go. Does that make sense? Does everyone feel okay about the process?
Yeah.
All right, Afe, so want to do the windlass, the windlass?
Yeah.
I didn't know that word until
Windlass?
I saw this diagram and I was like, what is that? But it's a real thing. It's like a winch.
Yeah.
It's like a little 43. This is another really famous application of related rates.
Windlass. You're like winding it. And it's a lass, I guess.
Windlass.
Windlass. I gotta bring that.
I think of an Irish person saying it every time I see it. You see it on a normal basis. Yeah, like you see it in some fantasy maps.
Oh, do you?
Yeah, I mean, it's actually really big in like
Books.
it actually comes up a few times in like the brother band, and I guess Raiden for Frenches too, since it's in the same world basically. But yeah, I feel like it's like that Ember book, the Ember, like Ember in the Ashes. Oh, maybe I that one. I don't know, but it's also in this other book like called Lioness that I cannot find for the life of me. I remember reading it like as if it's for a fever dream in junior high. Like it's like this weird time like in my memory where I'm just like it's all weird and warped. I want to read that book again, but I can't find it. I appreciate your book.
Okay.
It's so cute. It's a tiny book.
So this is a really popular style of problem that you'll encounter when you learn about related rates in calculus. Is, spoiler alert, we're going to use the. This is going to involve the Pythagorean theorem.
Whoa.
Mind blown, right? It's Mr. Bean hater. Pythagoras, he hated beans. okay?
Why?
Potato.
Why is this a known fact? Why do you know this now?
Savage.
Wait, I thought there was gonna be a punchline.
Yeah, Pythagoras had a whole like sort of cult, and part of their belief system was you shouldn't eat beans. Once you die, it's something about I think it like corrupted your soul or made you lose your soul or something.
The damn
It made you fart out your soul. I don't know what it was. He's a savage. If you want some fun reading, read about the quirky beliefs of Pythagoras and his. Back then, all those ancient Greek dudes, philosophers, mathematicians, they all went pretty crazy. You ever heard of the guy, what's his name, Diogenes? He was like a total lit savage. I kind of like how you've heard of him. He would just go around and be a total lit savage like all the time. Like just would take top on everyone.
Can you explain in
There's a famous story where Diogenes, he just rejected like all societal norms very much, but he was also like a genius. There's a famous story where Alexander the Great is coming through town. Who, if you don't know, that was like he was basically like imagine Charlie D'Amelio plus I don't even know Logan Paul or something combined into one, the ultimate human. Like they thought he was a god. Anyway, Alexander the Great conqueror, not the only conqueror, is like. He's heard about Diogenes. He's like, Diogenes, you are such a lit savage. Like, if I could do one thing for you, like, make a wish and I'll grant it. And he just says, like, get out of my sun. Like, he was blocking the sun. So he's like, can you get out of the way? Anyway, so.
Classic.
And there's another story where they're like debating over what is a human. And they're philosophers. They're all like, they're trying to boil it down into the most essential essence. And they go, the thing with 2 legs and no fur, I think. That's what they come up with. If you have 2 legs and no fur, you're a human. And Diogenes, what? Exactly, yeah. A featherless and frozen. Exactly. And then so he plucks the chicken and he goes, I present to you a man.
I think they would be best friends. That's
Yeah, they say he would just like be homeless and just like bark at people like a dog.
I bark at people.
Yeah.
Oh my god.
Just look him up if you want. He's
Classic. Let's
Huh?
I bark at people.
Nobody lives today.
I
I bring back to life.
I just yuck.
Put him in front of
Yeah, so it's fascinating to read about these people. That guy, read about Pythagoras, and then read about Isaac Newton. If you want a real weirdo, Isaac Newton, who him and Leibniz invented all this stuff we're doing. But that dude, Newton was an absolute nut job. Arguably the greatest genius who's ever lived, but completely whack. He was total whack.
I feel like you have to substitute something in order to get this.
Anyway, okay.
I'm learning all these things.
You're smarter than Newton. Yep. So, okay, the dock is, so this is like the dock up here. And so the dock is 15 feet above the water level. And then the boat's over here. And so you can see, and here's the rope. This is like the cable, right? And so it says, let's parse the sentence here. It goes, there, we already have the 15 label, great. It's pulling in the rope at a rate of 30 feet per minute. So how do if the rope is being pulled in 30 feet per minute, how do I write that? Z prime is -30. How do you feel about that? Right, so Z is a quantity that changes over time. If Z is decreasing, right, the boat's being pulled in, so Z must be decreasing, so its rate of change is negative, and then it's telling us that it's 30 feet per minute. So maybe you guys maybe you guys understand this confusion, but a lot of people want, like, they have a feeling they have to put like a T in there. It's pretty common, like, misconception. Oh, it says feet per minute, so I have to have a T involved. Well, there is a T involved. It's just over here. The change in Z over time. So you're wondering, where's that T? Where's that time? It's in here. So, are we okay with that?
Yeah.
Yeah. Okay. Then it says, at what rate is the boat approaching the dock? So what are we looking for? We're trying to find because the boat's not gonna lift up, right? The boat's not gonna travel. Yeah, the boat's gonna travel along this axis, so we're looking for x prime. What moment do we wanna know x prime?
Z is equal to
When z is 25. Okay, so do we feel okay? Again, I think this is the hardest part of the process, is identifying this stuff accurately. No questions? Can you proceed?
Yes.
Okay, so, first, what's the relationship between our quantities? X squared plus 15 squared equals z squared. Okay, so, I don't need to rearrange that or anything, right? I can just take the derivative as it is. That's sort of the beauty of implicit differentiation. So, a derivative of him would be 2xx prime. Derivative of him would be 0, constant. Derivative of him is 2zz prime.
Oh, yeah.
Caleb's jokes are sort of growing on me. It's kind of like an acquired taste, like a fine wine, you know?
Oh, I like being prepared.
Yeah, it's at first you're like, oh, this, I don't know if I like this. Then I know after years of. Yes, a nice French cheese. Okay. Does everyone see why we are rearranging it that way?
Yeah.
So the 2 is wide out. I'm trying to find x prime, so okay, now let's plug in everything we know, and hopefully we have enough information. The z value. Oh, I'm sure I know that one yet, so let's leave that blank for now. You know z prime, right?
Wait, is it Z 25?
Because we're trying to find the right.
Oh, yeah. I was testing you, obviously.
Just testing it.
We know x, though. I guess maybe that's what I was thinking of. We can figure it out, though, so to find x, what you gotta do is maybe just go, well, when this is 15,
Bless you.
and this is 25,
Bless you.
there's a sneaky way to get this, which is to notice it's too savage. Yeah, notice it's a 3, 4, 5, right? Because this is 3 times. Basically, take this triangle and multiply everything by 5 and get that triangle. Or just do Pythagorean theorem. It doesn't matter. No matter what you end up doing, you're going to find this is 20. Does that make sense?
Yeah.
So 20. So, what do you get? You get 3 halves here, so negative 75. 2s. Or in this, I think in this context, it probably makes more sense to write it as a decimal.
Do you like my hints?
Would it be per?
I should make it more Voldemort. Beautiful.
Do you find that answer surprising? I do.
Why?
Because, I mean, I don't know, you might think intuitively that since x is smaller than z, its rate of change would be smaller, but we find that's not the case. Right? Z, the rope, it's shrinking by 30 feet per minute, but x is shrinking at 37.5 feet per minute. So I don't know. That's, huh? You'd be left with what?
Even when the boat reaches the dock, you still have about 15 feet of rope.
Yeah,
Makes sense.
I still think that it's weird that the rate of change would bigger.
Yeah, I made a good point there, which is, so suppose.
But I guess we're only, I guess
He has to lose 10 feet of length in the same amount of time that he has to lose 20 feet of length.
okay, yeah, that makes sense.
You can see that it's very much non-linear, right? As as z shrinks, z and x are both changing under this relationship, and so it's not a very simple relationship that's going on. Okay. Burrito.
I know, I think it's interesting. I'm sure you do. Fascinating. Fascinating. Also, look at this. Look at this one. Look at this girl. She's very pretty. Like, wow. There's this one, you know, there's this one, and then there's like this one. Like, what the heck is that?
That's not boing.
No. Opposite of boing.
There's a really interesting calculus problem. It's a little bit more challenging than that. Oh, it's quite a bit more challenging actually, but it's a bit outside the scope of this class. But if you're interested, if you like kind of like paradoxical, weird sort of things, if you look up the ant on a rubber band puzzle,
Oh, yeah.
it basically says you have this rubber band, and I might mess up the statement of the problem, but if you read up on it, you can read about the problem without getting into the math. Really, it's pretty interesting. But you have like a rubber band, a theoretical rubber band, and you got here's Mr. Ant, and you say every minute an ant travels, say, a foot, but the rubber band stretches an additional 2 feet every minute. So the rubber band is stretching faster than the ant is walking. And then and of course, it has to be a theoretical rubber band that's infinitely elastic. But it's like, will Mr. Ant ever get to the end?
That reminds me of that idea that you can never, like, cross a room. Oh, I hate that. It makes me so mad. Oh, that makes me so mad.
The tricky part is you have to, well, I think the result is that the ant does get there. It takes a really long time, and it's
You're
because
obviously upset.
every time the band stretches, it actually pulls the ant forward a little bit. Exactly. It's a very counterintuitive result.
I did listen to the radio the other day. They give those fun facts on Fridays or something on the river. And it said that a famous, I couldn't remember exactly the name of this, but something like the sheep problem. It's like a famous math problem.
The sheep.
I don't know. But all I remember is somebody eventually solved it. It's been like this huge debate.
Oh, the sheep on the road?
Yeah! Somebody finally solved it. And it was very fascinating. I don't know.
I think I saw the
It
same article.
It's-
Yeah, you got like a sheep on a. I can't remember exactly, but yeah, a sheep is attached to a rope with a stake, and then it's how much area can the sheep raise. But then you have to have something like, I think what you do is you actually have like a circular, they're in a circular pen. You put the stake there, and like there's the rope. Here's Mr. Sheepy. And so it's like, well, how much can he raise? Well, he can raise this circle, obviously, and anything inside of it. Then you calculate. But I think they solved was like a general case of like n dimensions or something.
I don't know, it might have been something different, but I remember it was some like weird problem that they've been arguing about for a long time.
We're on the same page. There's another one you can invert it. You can put the fence like this, put Mr. Sheepy on the outside. And now it's even weirder, because now he can, as he comes around this side,
I question that.
well, like, oh yeah, I don't know why you, like, calculating that area is not an interesting problem too. It's how much can the sheep raise? He's free range, he's free
Why do we
range.
have 300 watermelons? I don't know. But suddenly we all do. I love those. I love those videos.
What's that? All right. Another.
Oh my god, have you seen the video where it's like, I'm judging you, damn it?
Another famous problem here. Mr. Cone.
Mr. Cone.
Mr. Conehead. Okay. So, 46. it says, consider a conical container of radius 20. Radius is 20. And the height is 40. Okay. It's a container though, and we're gonna pour in water from the top. So water is gonna pour in, water. And the question is, at what rate is the water level in the container changing when the water level is 30 centimeters? Okay. How do we feel about that? Does the question make sense? You okay, Cooper? You make it, bro? Someone give Cooper some soda pops.
I'm fine.
He needs some Monster Energy soda pops. Okay. So here's the question. Let me ask this. Here's a simple question. When the water pours in, what shape does the water form? A cone, right? Now, here's the trick. This cone that the water forms, let's say, here's the cone formed of water, so I'll kind of shade it, I guess. Okay. What is the relationship between, let's say this cone of water has, some radius and some height. So, okay, the volume of the cone of water is 1/3 pi r squared times height. But what's the extra constraint on this? This is the less obvious part. Think of it. So this is true. This describes the volume of the water, but think about it's in this container, right? This container has certain proportions. So the cone of water will have the same proportions as the container, right? Very good. What, Alyssa?
I feel like that's a go-to for her.
I think I heard you say the correct thing, and now that you're correct too. Yeah, it's a 1-to-2 ratio. Yes. What we're going to do is good question. It says, what are we looking to find? What are we looking for, H prime or R prime? We're trying to find, does that make sense when we're trying to find H prime? Does that make sense? So we're trying to find H prime at the moment when H is 30. Does that make sense?
Yes.
So here's gonna be a simple question. What's the radius gonna be at that moment? Yeah, 15, right? But more generally, what I could say is that for this cone, the height is always equal to double the radius, right? Just like in the previous problem we did. But this time, do you see how this is a big clue that I would like this formula to only have h's in it on the right side?
Yes.
So then what I want to do is replace all the r's with 1/2 h's. This is the sub I want to do here. Is that okay? So the volume of this cone is really V equals 1/3 times pi times half of h squared times h. Right? I'll simplify that one more time, I guess. Because this is a little bit weird looking. So 1/2 squared is a quarter, and a quarter times a third is 12. So it turns out that for this particular container, the cone of water inside has this formula. And again, it's only because we knew that the radius is half the height. Okay, derivative time. But wait, this makes us happy because we go, oh, we don't have to use the product rule anymore. Like we just have a simple chain rule application. So 3 times a 12 quarter, so quarter pi, h squared on the h prime. Yeah. All right. They gave us a bunch of information in the problem. How big is v prime to this question? 50. So this number here. Well, that was 50 cubic centimeters per second. Fun trivia fact. What's the more common name for a cubic centimeter? Yeah, very good. A milliliter. Yeah, like a Lil Wayne song, a milli. I love that song. He tells you how to use the metric system. It's one of the most educational pieces of music in history. Nothing is blah 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 blah.
No, I liked that one video in Dizerov's class where it was Sweet Caroline, but it was like mass and
Oh, I don't know what I'm doing.
Moons are away. Gravity's full of the ocean. Oh yeah.
That song's a slap.
That is a good song.
It is a slap.
Yeah.
Oh, what was that
Cleopatra one that we watched.
Oh god, that was so bad.
I don't know.
So here's one where I think the order that you do this arithmetic in kind of matters because just for simplicity's sake, but let's just send that 4 over to be buds with the 50, so that's 200. And then divide by the pi, okay, there's the pi, and also divide by 30 squared, which is 900. Shout out to Tony Hawk. So funny. Okay, so anyway, 2 ninths. So it's 2 over 9 pi. Not to be confused with 2 ninths of pi. Those are not the same. There you go.
Units.
Oh, units! Let's see, what are they? They're talking about cubic centimeters per second, so this better be
Centimeters.
it's centimeters per second. Thanks for reminding me. I keep forgetting about the units.
Oh, lame.
Lame, sad. Wrong, sad. I forgot the units wrong. So, here's a question for you. Does it make just like physical sense why the longer this process goes, the smaller this h prime gets?
Yeah.
Because like think about when the thing first starts filling up. You know, if you had 50 milliliters, right? That first 50 milliliters might give you a few centimeters. But now, since it's a wider container, that next 50 milliliters isn't going to give you as much additional height. Make sense?
Yes.
Can you put your TikTok away, please? Thank you. All right, the last thing we got to cover, guys, is it's a bit of a return to more abstract stuff here. We're going to talk about a point traveling along the curve. So hopefully you've seen enough of like, okay, related rates. You can use related rates to describe a physical system, something that's real, or you can use it to describe, say, slopes of a curve. And now we're going to see a point traveling along the curve.
Lit.
All right. So first I want to give you just a general, very simple introduction to this, which is like, look at say a really simple thing like a parabola. I'm just going to draw the right half of it. So think about a point traveling along this curve. Okay, so this is some point. A point has an x and a y coordinate. And we're going to say that, say it's constrained to move along the curve y equals x. Okay? Here's just a purely intuitive question. If I told you that this thing is traveling in a way such that, say, x prime was 3, just suppose that was the case. Meaning, say it was traveling 3 units to the right every second. Does it make sense why over time y prime will be getting bigger and bigger? Because like take the first second for example. During the first second, say it goes from 0 to 3, think about the y values. It went from 0 to 9, so it gained 9 vertical units. And think about the next 3 seconds. So at times 6, you'd be up at 36. So during the first second, I might have misspoke there and said 3 seconds. Oh, sorry, I'm what am I doing? Oh no, yeah. During the first second, you get to 3, 9. And then during the next second, you get to 636. So during the first second, he traveled 9 units up, y increased by 9. During the second period of time, he gained 27. Does that make sense?
He's 80.
Now you can see just mathematically, watch what happens. Y prime equals 2x, x prime. So you can see that y prime gets bigger as x gets bigger, right? Okay, so the basic idea makes sense?
Z.
Okay. 48. So, what shape is that?
It's like a, yeah, what shape is
What shape is that?
That thingy.
that one?
That one.
Well, that looks awfully, if you did 2 steps, you could get x squared plus y squared equals 25, right?
Yeah.
Think about,
I guess.
what if I started you off with x squared plus y squared equals 25? You subtract the x squared over, but then, here's the thing though, if this is a circle, right, this actually omits the bottom half of the circle. This is actually a function. This is not a function, this is a function. This is not a function, this is
So
a
it's half of
function.
a bird.
The bird is
No,
what?
it's a semicircle. Ah, what's the sunrise?
Semicircle.
That's what I said.
Well, clearly.
Well, I thought we did the same thing. No, I was just going there, not. Oh.
What's the radius?
And
9. This is also fun. Okay. It says that
Like a sunrise.
a particle or a point is moving along this curve in a way such that its x coordinate is increasing at a rate of 2 units per minute. Right, that's a complex statement there. So you gotta understand that. What it's saying is a point is moving along this curve, okay, so it's actually moving along the curve, but it's doing so in sort of a weird way where it's gaining 2 units in the x direction every minute. Does that make sense?
Yeah.
Okay, does it make sense why that, let's say you started here. Which is not necessarily true, but say you did. That first minute, you would have traveled quite a decent distance, right? Because look at all that vertical distance he has to cover just to move over, like say 1 unit, right? But then later on, there's not much vertical change. So anyway, it says at the moment when the x coordinate is 3, it's here. What is the rate of change of the y coordinate? By the way, is this answer going to be positive or negative? See, he's moving along this curve, right? At this moment, is his y value going, is it decreasing or increasing? It's decreasing. He's traveling in this direction, so his y value is decreasing. So we're expecting a negative y prime. This is our expectation. Y prime should be negative. So let's do the math. Y prime is equal to, you have square root of u here, right? So it's going to be, well, sorry if I'm repeating myself millions of times, but this is a pretty common result that comes up over and over again, right? the square root of u will give us u prime over 2 of u.
Yeah.
Okay, so what's our u prime in this case?
2x.
Negative. Very good. Don't forget that x prime. That's important.
But since it's 1/2.
And over 2 root u. Are we okay with that? The 2's cancel immensely, of course. With what? Yes, that's what that is.
Bro, what did?
So did you do the 1/2?
Oh, yes, that is the 1/2.
Okay. Yep. That's good. That's the same as this, yeah. So that's just certainly what you said is true. I just like to. This is one that comes up so often that I'm like, okay, you can kind of just. It's a special case of 1/2 power. Okay, so what should we plug in then? Well, first of all, the 2's cancel out. So get out of here. Get out of here.
Get out of here.
So the moment we're concerned with is when, so we're trying to find y prime when x is equal to 3. And they also told us that x prime is what? 2. So this is the information that's going to get plugged in. So value of y prime at the moment when x is 3 would be negative x value, which is 2, times x prime. Oh, sorry. I'm done. What's x again?
3.
3. Negative 3 times. This is silly goose. Okay. Square root of. Okay. What's 25 minus 9? 16. And his square root, of course, is 4.
Wow.
And so we get this really nice answer. Units, of course, just being units per minute.
What is it?
Really?
Sorry.
I got it.